wasn't as easy as I thought. Yeah. Huh.
Now we're using a chemical chemistry.
I guess that's why it's still up. I would have thought you would just pull this up and then push it. Oh, there we go. There we go.
I have to steal one of these desks for my home.
Just when you think there's nothing new in the world.
Desks. So this one's flipped.
But flips too.
Crazy. I don't know what they're doing in here. I don't think I want them.
Okay, we'll go ahead and get started. Can you see the slide and hear me okay? Okay, thank you. All right, so what we're going to talk about today is nuclear chemistry. So as you know, this is the last lecture of the semester. So I want to just say thanks for sticking with it all semester and I've enjoyed teaching you. Hopefully you enjoyed the class. As I said, today we're going to finish with chapter 21, nuclear chemistry, talk about that a little bit today. I did want to remind you what we have coming up though. So while there's no more lectures, we do have an exam on Thursday of this week, and that'll cover chapter 21 and chapter 24. And then the following week, the final exam is Tuesday, May 4th at 8 a.m. And that, as all our exams have been, that'll be online on Canvas. So this week, log on to Canvas on Thursday and take the exam covering chapters 21 and 24. And then next week on Tuesday, May 4th at 8 a.m., log on and take the final exam. The final exam is comprehensive, so it does cover everything. In terms of how long it'll be similar to a regular exam in terms of length. I just want to remind everyone that in the class, I do drop the low quiz for the semester, and I do drop the low exam. I do not drop the final. So if the final's your low, you're stuck with it. But I do drop one of the lowest of the 5 exams. If you missed a quiz or you missed an exam for some reason, that counts as your drop. So any questions about any of that stuff? All right, well, let's talk about nuclear chemistry a little bit. So what you'll see is, as we kind of go over some of the basics of nuclear chemistry, is that it's really pretty different chemistry from what we've been studying this year. Because so far, we really haven't done anything with the nucleus in terms of what happens there. It's been pretty much those valence electrons, those bonding electrons, and talking about the impact of that and what happens with those. So nuclear chemistry is kind of a different beast, so to speak, in that you're looking at the nuclei. And if you recall, when we talked about regular chemistry type reactions and interactions, we might have rearranged how the atoms were bonded and things like that, but we never changed the elements. In nuclear chemistry, what you'll see is that you actually change elements. So you're changing the nucleus. So instead of just fooling with some of the outer shell electrons and changing a bonding or energy absorption or something like that, you're actually taking an atom, of a particular element and changing it to another element. So it's kind of different. All right. So I want to just refresh your memory on something that we've talked about in the past, and that is kind of some of the symbols that we use to represent mass number, the element, atomic number. So on this slide, we see in red, we see carbon, and then of course, when we write these, that's the symbol for the element. In blue, the number on top, in this case, it's 12. That's the mass number. So that's the atomic mass number. And remember that atomic mass number, represents the number of protons plus neutrons. So remember, the atoms get their mass from the protons and the neutrons. The number in green, below the 12, that's the atomic number. And that tells us the number of protons that are present. If it's neutral, it's also the number of electrons. So the number on top is the mass number. That's protons plus neutrons. The number on the bottom is the atomic number. That's protons or electrons. And so a term that we haven't used before is nucleon. And nucleon is just what we're saying the nucleus is composed of, and that's protons and neutrons. So we'll be looking at elements quite a bit like this and focusing on the mass number and the atomic number when we talk about this nuclear chemistry today. And that'll factor also into how we balance the equations for these nuclear type of reactions. So balancing equations for the nuclear reactions is a little bit different than the redox or the regular chemistry balancing. But conceptually, it's kind of the same thing. You got to do a lot of counting and make sure you're equal on both sides of the arrow. But we'll get to that in a moment. Okay, so now, a term that we have mentioned a little bit, but I want to mention it again because this is a big deal in nuclear chemistry, is isotopes. So atoms of the same element don't necessarily have the same mass. So the reason for that is they'll have different numbers of protons, or rather neutrons. So because they have different numbers of neutrons, the mass number will be different. Because remember we said the mass number is protons plus neutrons. And once again, that mass number in this slide is the one in blue, it's the 12. And as we said, that number on top, mass number, protons plus neutrons. So if the mass number is different for a particular element, it's because it's got different numbers of neutrons. Here's an example of 3 isotopes of uranium, 234, 235, 238. What that indicates is that each of those have a different number of neutrons. Some nuclei can change spontaneously and emit radiation. And nuclei that can do this, so elements that can do this, we say are radioactive. And those radioactive elements are called radionuclides. And there's several ways that these radionuclides can decay to form a different nuclide. And that's what we'll be talking about here. And we'll be writing nuclear equations to show how that occurs. And one of the things that hopefully you picked up on as I talked about this stuff is we're actually forming different elements, okay? So as these radioactive materials emit radiation, you often have a new element. And that's where it's different than the kind of chemistry we've talked about before. We've talked about reactions and things like that where you may form a different molecule, but we haven't really changed atoms. We've just rearranged them. In the nuclear stuff, you're actually changing the elements to something else. Okay, so when we talk about these nuclear equations, what we're balancing is slightly different. When we did our previous chemical equations, we were trying to make sure that we had the same number of atoms of the elements on the left-hand side and the right-hand side of the equation. So we also were trying to make sure that the charge on each side of the equation balanced. And so with the nuclear equations, it's a little bit different. You're still balancing stuff, but what you're concerned about balancing are the atomic number and the atomic mass. those numbers are what need to balance. And we'll see some examples of that in a little bit. So notice what I didn't say. I didn't say we have to balance the atoms, okay? So we're not going to be balancing the atoms in these nuclear equations when we balance them. We're just trying to balance the total of the mass, atomic mass on each side, and the total of the atomic number on each side. So a lot of times I'll tell you there's a particular slide that I think has a lot of value, and this is one of them. And so what this slide is telling us in this table is it's telling us a few of the types of radiation that one of these radionuclides can emit. And so if we look at the table, we see across the top here, we see alpha, beta, and gamma. So those are the symbols for alpha, beta, and gamma. And those are three common types of radiation that are emitted. What we see in the next row is we see the charge associated with it. Alpha +2, beta -1, and gamma 0. Then we have some masses. And then the next two are pretty important. So we see the relative penetrating power. So what we mean there is, we see, for instance, that gamma is 10,000 and alpha is 1. We're just saying that gamma radiation has 10,000 times the penetrating power that the alpha does. And we see the rate, we see the beta is 100 here. So 100 times more penetrating power for beta than alpha. So what this tells us is that depending upon what your application is if you wanted something that has a lot of penetrating power and goes into the tissue or whatever, then you'd want to use the gamma radiation. If you didn't want to do that, you want to use perhaps alpha radiation. So this is just telling us that for these types of radiation, you have a pretty wide range of penetrating power. And this penetrating power oftentimes is used in medical things and stuff like that. The other thing that's important to note is this next row across and the nature of radiation. And so we see that for alpha, it's really a helium nuclide. And so we see that by the atomic mass of 4 and the atomic number of 2. Beta is we're talking about electrons. And that makes sense because we said the charge was -1. Gamma, remember we said no charge, no mass. That's because it's a high energy photon. So 3 pretty different types of energy there. Helium nuclei, electrons, high energy photons. So make sure that you understand the differences here between alpha, beta, and gamma in terms of charge, in terms of mass, in terms of penetrating power, and in terms of what type of radiation it is. What we're going to do now is look at these and a couple other types of emissions in a little more detail. So when we talk about that radioactive emission or decay, alpha decay, beta decay, which we just mentioned, gamma emission, and then 2 others that we'll be talking about a bit is positron emission, and then something called electron capture. So when we start talking about types of radioactive decay, what we're talking about is potential changes in atomic number and potential changes in mass number. And so for these types of processes, let's look at what that means. And this is another table that I think summarizes pretty well what goes on. So if we take a look at the first one, the alpha emission, we have a nuclear equation that we're going to go through, but let's hold off on that a second. And let's look at change in atomic number and change in mass number. We're saying that for an alpha emission, the change in the atomic number is a decrease of 2. So the change is -2. Remember, atomic number is that number, is the bottom number when we did that writing of the symbol with the atomic mass and atomic number. So that bottom number will change by -2 if we have alpha emission. So what we're saying is, whatever element that is, after it has the alpha emission, it's going to be a new element then. And it'll be an element that is 2 lower on the periodic table. So pretty interesting, I think. We're not just doing a reaction, we're actually changing the material from what it was originally to something that's two atomic numbers less. And so we have to look that up in the periodic table unless you've got it memorized. The other one is change in mass number. Remember, the mass number is that the top number, and that's the protons plus neutrons. Well, we have a change there of -4. So for alpha emission, you have change in atomic number and change in mass number of these values. And if we look at the nuclear equation column, we can see how these changes impact things. So on the left-hand side of the arrow, we have the compound we're calling X, or an element we're calling X. A is that mass number, Z is the atomic number. And we see that when we have the alpha emission, what we wind up with is A -4 for the new mass number and Z -2 for the new atomic number. And we see now it's no longer X, but we're calling it Y. Just a different, and that just signifies a different element. And so through this alpha emission, we've changed what the element is. And then we have plus the helium 4-2. And now what we would do is we would go and we would check to make sure our mass numbers add up and balance on the left-hand side and right-hand side, and our atomic numbers on the left-hand side and right-hand side add up and balance out. So we'll go through some examples of this in a little bit, but that's in general how you do that. The beta emission is similar, except in this case, we see the change in atomic number is +1. The mass number doesn't change. And so if we look over at the nuclear equation for the beta emission, we see that the Z value now increases by 1. So we would have to go and look up on the periodic table to see what that next higher element is. And then we would change to that. And then remember, this was the one with electrons, beta is. And so we have this electron with the -1 in the atomic number change. So remember that atomic number, we said it's protons or electrons, but that's when it's neutral, they're the same. So we've had a change in that electron there. Positron emission, that's a case of where you change the atomic number by -1, the mass number doesn't change. So we would reflect that over here in our nuclear equation. And then finally, the last one is something called electron capture, which is a little bit different. It's not an emission. So we had emissions for the first 3 where we had something show up on the right-hand side of our equation. In this one, electron capture is just what it sounds like. The nucleus is able to capture an electron from the electron cloud surrounding it. And so there we have an electron on the left-hand side of the equation. And so on the right-hand side, we see that atomic number decreases by 1. So this is in general how these 4 things impact our nuclear decay reaction. So let's take a look at things in a little more detail. So here's the alpha decay one again. So Alpha, losing that alpha particle, which we said is the helium-4 nucleus. So 2 protons, 2 neutrons. And so we can write that here. In this case, we have U-238. If we're trying to balance things out, we're going to be losing the helium, 4 for the mass, 2 for the atomic number. We see that written in our equation. And so now we have to balance this. So if we're 238, let's focus on the mass first. If we're 238 on the left-hand side, we've lost 4, so we've got 4 on the right-hand side for the helium. So then to balance out 238 on both sides, whatever the new element is, has to have a mass of 234. If we look at the atomic number, we have 92 on the left-hand side. We have a 2 from the helium on the right-hand side. So to balance out, we need something that's 90 on the right-hand side. So we look at that, we have 92 on the left, 90 plus 2 for a total of 92 on the right-hand side. And so now we're balanced out. We've balanced our masses, 238 and 238, that's the numbers on top. We've balanced our atomic numbers, 92 on the left, 92 on the right. And so now we have a balanced nuclear equation. What we still would need to do is, what element is 90? And so we would have to go to our periodic table and look that up, unless you have the note off the top of your head. I know I don't. And so in this case, it's thorium, TH. And so one thing you'll need when you take the exam on Thursday is make sure you have a periodic table handy. Make sure you have a list where you can quickly look up, okay, in this case, what element is 2 less on the periodic table, okay? So what you notice we didn't do is we didn't balance the atoms. No balancing of the atoms for these nuclear ones. And that was our big thing before. Remember, we were always worried about balancing, making sure we had the same number of carbons or hydrogens or whatever on each side. We don't do that with the nuclear stuff. What we're interested in balancing are the atomic masses, those numbers on the top, and then the atomic numbers, those numbers on the bottom. So we'll have this same kind of approach for all of these. So now let's look at beta decay. So we said beta decays, losing that beta particle, and basically it's losing an electron emitted by the nucleus. And so that's where there's 2 ways you can write that. The beta symbol with a 0 and a -1, or electron symbol with a 0 and a -1. So what it's telling us though is that our atomic number is decreasing by 1 because we're losing that. We're losing that electron, so our atomic number is changing by 1. So if we go to balance that, so here we have iodine on the left, 131 is the mass, 53 is the atomic number. If on the right-hand side, we've generated a -1 on the atomic number, then -1 plus something has to equal 53. That would be 54 for the atomic number. The mass is the same, 131 on the left, 131 on the right, because the electron doesn't have mass, so that's a 0 there. And so what we see is that because of losing that electron, the atomic number increased by 1 to balance it out to have 53 on each side. So we'd have to go to the periodic table and look and see what element is number 54 rather, and 54 is xenon. So that's how we would balance that out. Gamma emission. Gamma emission, remember we said that that is a photon. And so it's not uncommon to get this But in terms of balancing things, it doesn't have an impact because it doesn't change the atomic mass and it doesn't change the atomic number. So we don't have to worry about balancing the nuclear equation because of the gamma emission. Positron emission is another one. So some nuclei decay by emitting a positron. A positron is just the opposite of an electron. So remember, electron was a -1 that was emitted. Positron is a +1 that's emitted. So in this example here, we have carbon, atomic mass 11, atomic number 6. If it emits that positron, then it's emitting 0 with a +1 on in terms of the atomic number. And so what we have to do is find out if we have +1 on the right-hand side, +6 on the left-hand side. That tells us that we need +5 on the right-hand side for the atomic number, so that our atomic numbers match up, 6 and 6 on the two sides. The mass is still 11. And we would go and look at our periodic table and see, well, what element has an atomic number of 5? In this case, that is boron. So then we would have things balanced. So our mass is balanced, 11 and 11. Our atomic number balances, 6 and 6. Okay, electron capture is another one. That's the one we talked about where the nucleus is able to capture an electron, absorb an electron from that electron cloud that's around it. And so in that case, instead of having what's going on the right-hand side of the equation, it's on the left-hand side of the equation. So in this case, it's the electron, so it's 0 and -1. So for the rubidium, we see that's 81 for the mass and 37 for the atomic number. 30 plus 37 and -1, that puts us at 36. And so we would look up and see what the element is at 36. And that's what our new element is in the electron capture process. So kind of a common theme in these balancing these equations, these nuclear equations. And so if you think about what we did is, we thought about, well, what's the process that's happening? Is it alpha emission, beta emission, electron capture, gamma, whatever it is? Then we would think back to the table and the information we knew about, okay, if it's this type of emission or whatever the process is that's going on, then we know how that impacts. First of all, does it impact the atomic mass? Most of the time, unless it's no, the exception is that alpha emission. So we take care of that first. Then we look at the atomic number to see, is it gaining 1? Is it losing 1? Is it 2? Is it just what is the impact of the emission on the atomic number? And then we go and we make sure that the mass is balanced on the left and right-hand side. And we make sure the atomic number is balanced on the left and right-hand side. Once you've got all that balanced, then if that atomic number has changed, and for most of these it does change, if it changes, then we need to see, okay, what element is represented by that new atomic number? And once we do that, then we can write that in, and then we have our equation balanced. So same kind of idea. We don't worry about balancing the atoms in these equations because we're literally changing what the atoms are. And that's a big difference in terms of how when we balance stuff previously, whether it be the redox or the typical chemistry balancing. Okay, so when we think about nuclear stability, any atom that has more than one proton, so in other words, anything but hydrogen, you have repulsions between the protons in the nucleus. And that kind of makes sense because we always said before, opposites attract, same charge, you get some repulsion, you get some conflict. And so the protons are going to be positively charged, they're all positive. There's that repulsion that can take place. So you need a strong nuclear force to keep it together. And what helps and plays a big role in stabilizing things in the nucleus are the neutrons. And so there's some general rules around the number of neutrons and how that impacts stability, and also the ratio of those neutrons to protons. And so we're going to talk about that a little bit here. So the plot that you see here on the right-hand side of the slide, let's take a look at that for a little bit and talk about that. So on the x-axis, we have the number of protons. On the y-axis, we have the number of neutrons. And then what's plotted here is that ratio of neutrons to protons. The red line that you see drawn represents if there's a 1-to-1 ratio of neutrons to protons. So in other words, if you take the number of neutrons and divide it by the number of protons, you get a value of 1. How do we figure out what the number of neutrons are? Remember, we said the atomic mass is the number of neutrons plus protons. We said the number of protons is the atomic number. So if we wanted to find the number of neutrons, we could take that atomic mass number and subtract the atomic number. So that would give us the number of neutrons in whatever element we're looking at. Okay, then we could take that number of neutrons that we got from doing that math and divide it by the atomic number, because remember, once again, the atomic number is the number of protons that we have. And that's how we would get these ratio values. And there's a couple things that we know from this. One is that for smaller nuclei, so values down here of 20 and less, so at the very bottom of our red line down here, we know that that ratio is pretty close to 1-to-1 for the small ones. Okay, so we have alignment there. Now, as the number of nuclei, as the nuclei get larger, you need more neutrons to stabilize the nucleus. And so when we look at this graph, we see, as I said, the red lines are 1-to-1 ratio, but this kind of yellowish area that you see going up, that's what is kind of happening in reality. Okay, it starts to diverge from that 1-to-1 ratio. Within the yellow area, you see kind of like a dark shaded area kind of going up. And that dark shaded area is something called the belt of stability. Okay, so for me, I always think that sounds kind of like a cheesy science fiction movie, but we've got the belt of stability here. I like it. And so what the belt of stability is telling us is that if something lies along that kind of darker blackish region there within the yellow region, that the nuclides are stable, okay? The other thing that we get from this is that if it's higher than that belt of stability, we're going to have some instability. If it's lower than it, we're going to have instability also. We'll talk about what that instability is. But what you see here, you see a couple of things on this plot. We see about midway up that neutron-proton ratio for the stable ones is about 1.4. we go higher up to the top, it's about 1.52. And so we see that ratio as we get to the bigger nucleus, it starts to shift more towards neutrons. And that's what we say. You get to the bigger nuclei and you need more neutrons to kind of stabilize things. So once again, looking at our belt of stability, if we're above it, okay, if we're above that, then we have too many neutrons. And so to stabilize things, we get decay, and the decay is we emit beta particles. So we emit that beta. So if it's below the belt of stability, then we have too many protons, and those nuclei want to become stable, and they do that by positron emission or electron capture. So once again, if you're along that belt of stability, then things are probably pretty stable. If you're above or below, you're introducing, for two different reasons, but you're introducing some instability. And things will happen in order to reestablish the stability. I think of the stability kind of like when we talk about equilibrium and the equilibrium reactions and stuff. That's something that you see is in common with these things, is they want to get to their most stable or favored state, and they'll do things to achieve that. And so that's where this belt of stability and kind of understanding how that ratio of, of neutrons to protons factors in. A final thing is, if you get to the larger atomic numbers, and by larger we mean above 84, then you tend to get decay by alpha emission. So irregardless of what that ratio tells us, you get to the bigger ones and you tend to get alpha emission. So another thing that happens is, we've been talking about one thing happening, one emission or one electron capture or something like that, and having that change. You also can get what's called a radioactive decay chain. And here's an example of one here, where we start with uranium. And so uranium is up here at 92 at the top. And we see that it starts a series of transformations, okay? And so the ones with the blue lines are alpha emission, and the ones with the red lines are beta emissions. So you have the uranium that starts and it keeps going, but it doesn't just do it once. We've got a bunch of steps here, as you can see, until it doesn't stabilize until it gets to lead down here, PD down at the bottom. So we're at 82 for our atomic number. So we went from an atomic number of 92, and by the time we finished, we were at 82. And you can see the different elements it went through to get to that point. So this is an example of something where you get this decay change and have a series of these transformations before you get to one that is stable. When we talk about stable nuclei, there's a couple rules of thumb that we want to try and remember. One is, if you have 2, 8, 20, 28, 50, or 82 protons, or if you have 2, 8, 20, 28, 50, 82, or 126 neutrons, if you have either of those situations, you tend to get more stable nuclides. The other one rule of thumb is nuclei that have an even number of protons and neutrons tend to be more stable than nuclei that have odd numbers of those. So rules of thumb for stable nuclei, if you have one of the magic numbers, in terms of protons or neutrons, things tend to be more stable. If you have an even number of protons and neutrons, then you tend to be more stable. So we often talk about nuclear transmutations. And so you can induce these by having collisions. You can have some type of particle collide with the nucleus and then stuff happens. Okay, two ways these are done that you may have heard of are particle accelerators, also known as atom smashers, and a linear accelerator. And these are big things. There's only a handful of these in the world. You see them on the news periodically when they make some big discovery. And so the particle accelerators use magnetic and electric fields, and they basically make the particles go really fast, and then they run into each other. Linear accelerator is a different type of approach where you have these tubes of different lengths and charges, but the idea is the same, making the particles move fast, and then you run stuff into them. So kind of the same idea, two ways of going about carrying it out. You may have heard of a cyclotron that uses some magnets to have the particles move in a spiral. There's something called a synchrotron, accelerates the particles in a circular path. Other ways to do these transmutations are you can use neutrons, and the synthetic isotopes that you see in medicine sometimes, a lot of times those are done by just bombarding the particle with a bunch of neutrons and then forming the new isotopes that way. There's also the transuranium elements. And so transuranium elements just means all the elements on the periodic table that are after uranium. And these were discovered by bombarding isotopes with neutrons. So in other words, someone didn't go out in a field and find a rock and find these elements. These were essentially created in the lab, but because they had a certain amount of stability, they're considered elements. Larger elements, ones that are above 110 atomic number, those are made by colliding big atoms with the nuclei of smaller elements. And so large elements colliding with smaller ones that have a lot of energy. So once again, similar to the other ones where isotopes were bombarded with neutrons, these are lab made as well. So in the nuclear world, there's a couple ways that you can express these transmutations. So let's take a look at the top one first, the top equation. So in this one, we have the nitrogen plus the helium that's bombarded. The key here is we have to make sure we balance. And so we look at our atomic mass. We got 14 and 4 on the top there for a total of 18. You look on the left, we've got 17 and 1, that balance is there. We look now at the atomic numbers, 7 and 2 for a total of 9 on the left-hand side, 8 and 1 for a total of 9 on the right-hand side. So in this one, we're bombarding it with an alpha particle. And so that's where the He with the 4 and the 2 comes from. Remember, we also could write it as the alpha as it is on the right-hand side here after the or. And then the P, that just stands for proton, okay? And so it's designated here as hydrogen with 1 and 1. The other way, which is more of a shorthand method that you see sometimes is down here below. We see that nitrogen, that's the target nucleus. The alpha is the bombarding particle. And then on the right-hand side, we have the product nucleus, which in this case was the oxygen, and then the ejected particle, which is that proton. So either way, we've got several ways here to write these. Actually, we have 3 ways to write them here. Any of those would be acceptable. It's just understanding kind of the shorthand version versus the ones that are drawn out a little bit more. The nice thing, at least to me, about the top one is it's a little easier for me to see that everything balances versus the shorthanded one down at the bottom. And even with the alpha and the one that has the alpha and the proton, the A and the alpha and the P on it, that one for me is, personally, I prefer to see instead of writing alpha, writing the helium, because then I remember it's 4 and 2, and don't have to think about it or anything. Okay, so one thing that people are probably familiar with is radioactive decay. And radioactive decay, most people are familiar with that when, you know, some archaeologist or someone will find an old dinosaur bone or something, and or old whatever, and they'll do carbon dating. And then they'll say it's, you know, it's 5,000 years old or 2,000 years old or 10,000 years, whatever. That all centers around radioactive decay. So let's talk about that for a little bit. Radioactive decay is a first order process. And so here we have the equation for that first order. And hopefully that looks familiar because we did the kinetics this semester. That's what we're talking about here is kinetics. The other thing that hopefully looks familiar, because we talked about half-life a little bit before. So here's the formula for that half-life process for this first order kinetics. And if you remember what we said half-life was the amount of time it took for half of the material to go away, basically. Well, it's the same idea with the radioactive stuff. We're saying that the half-life for this is the time required for half of the radionuclide sample to go away, to decay. And that's the kind of information that's used in this carbon dating and this other type of radiolabeled dating stuff that people do. So let's take a look at some common half-lives of some things that we hear about periodically. So in this table, what we have is we have some natural radioisotopes, and then we have some synthetic ones. So the natural ones would be the ones that just occur in nature normally. The synthetic ones would be ones that someone prepared through one of those reactions we talked about before, bombarding it with whatever's appropriate to get that. And so let's focus a little bit for a moment on the carbon here, on the natural. So we have carbon-14, and we see its half-life is 5,700 years. So that means if you have some material, if you let it sit there and then wait 5,700 years and then analyze it, half of it will be decayed. Okay, we look at some of these other numbers here. For like the uranium, we've got a 10 to the 9th, a 10 to the 8th. Pretty big numbers there. You go to the synthetic ones, the numbers are smaller, but when you think of it in years, you probably wouldn't want to be dealing with something that's even 28 years as a half-life. I don't remember what 0.022 is in years, but at least that one's a little more reasonable. And you see it's iodine, and sometimes you'll see iodine mentioned for radiolabeled like medical studies in that. So that has a much shorter half-life. On the right-hand side, what we see is we see the type of decay. And so we've got some alpha decay, alpha emitters here. We've got some beta emitters. Let's talk a little bit more about the use of the carbon. And so we said that it's first order kinetics, and the half-life is what we use because of that to give us a feel for how old stuff is. So as we saw on the table just a moment ago, carbon-14 is 5,700 years is its half-life. And remember the thing about half-life is you never technically get to zero because it's half, 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 half. But what you do get to is after a while, you get to where the number is pretty small and you can't really measure it. And for the carbon-14, that is approximately 50,000 years. So if it's older than 50,000 years, this carbon-14 dating isn't going to work for you because the signal, even though it's not zero, but it's too low and you can't really measure it. There are other isotopes that people use, uranium, lead, that are mentioned there. Those have different half-lives, and so you can see those a little bit longer. When you measure radioactivity, and what the definition of activity is just what's the rate at which something decays. And there's two units that are commonly used. One's the becquerel, which is 1 disintegration per second, and the other is the Curie, which is 3.7 times 10 to the 10th disintegrations per second. And that corresponds to the rate of decay of 1 gram of radium. The Curie is the one I think most people hear about. That goes back to Madame Curie, the lady who did a lot of this early radioactivity type work, actually died as a result of it. And so that unit is named after her. The other thing I want to just talk a little bit about is the energy associated with nuclear reactions. That's another thing that you hear about quite a bit is nuclear energy. So there's nuclear energy that we use on a limited basis, but there's also the nuclear energy. So the sun basically is a big nuclear reactor as well. That's nuclear energy as well. And so all this relates back to Einstein's E equals mc squared. And so what we want to do is just take a look at what we're talking about when we say there's a lot of energy here. So we have a calculation here. Don't worry about being able to do the calculation or anything like that. I'm not concerned about that. But the point of this example is to just show you a lot of energy when we talk about nuclear fission or fusion. And so if we look at the mass change associated with an alpha decay of 1 mole of U-238 going to thorium-234, that's 0.0046 grams, okay? So that mass change, so we're talking about 1 mole of material, which isn't very much, and we see that mass change is pretty small. The change in energy, if we plug our numbers in and do the calculation using that Einstein equation, we see that the answer is 4.1 times 10 to the 11th joules, or 410 billion kilojoules, okay, for 1 mole. And that's a big number. And the other thing to note is it's a negative number. Well, remember what negative means in these energy things? It means it's exothermic. So exothermic means it's giving that energy off. So this gives you just a feel for the amount of energy that's locked up in that nucleus. It's pretty amazing when you think about it. And this is why people have always been interested in nuclear energy, is that there's just a lot of potential energy locked up in there. If you could figure out how to safely manage it, you could really, solve a lot of your energy problems. So where does that energy come from? The masses of nuclei are always less than those of the individual parts. And this mass difference is called the mass defect. The other thing is that the energy needed to separate the nucleus into its nucleons is called the nuclear binding energy. And so here in this table, we have some mass defect values, we have some binding energy values. And so this is the information that we know that tells us that this is why we have all this pent up energy in there. And so when we think about the effect of that binding energy on the nuclear processes, let's look at this graph here on the right-hand side. And so on the x-axis, we have mass number. On the y-axis, on the right right-hand side, that as you go up, that's increased stability. On the left-hand side, that's binding energy per nucleon. And so what we see, though, is that the heavy nuclei gain stability when they split into two smaller nuclei, and that's called fission. The lighter ones emit energy when they're combined, and that's called fusion. So we kind of see this area down here to the left. That's where the combining is the more common occurrence that you can do, and that's fusion, and energy is released. On the right-hand side, for the bigger ones, you can split the nuclei, and then you release energy, and that's fission. So let's talk about those two processes for a little bit. At the beginning of the class, I talked about how we've been talking all year about chemical energy, and that was associated with, for the most part, with bond breaking and bond formation and things like that. Well, the nuclear energy, as we said, is really different. There's a lot more energy involved, and that's because you're actually changing the nucleus of atoms and converting them to different atoms. So just a much more, what I would call, extreme process. It's one thing to take some of those valence electrons and do something to it and break a bond or form a bond or something like that. It's a big deal if you're taking an atom and fusing it or splitting it or doing something to it so that now you have a different atom. And when we talk about fission, and fission is what is done in, like if you see a nuclear power plant somewhere, it's a fission reaction is what's going on. And that's where they're splitting the atom, as you hear people say. And here's an example of U-235, where you bombard U-235 with a neutron, and then you split it. And you wind up with 137 and 142, some other stuff there to balance it out, but it can go either way there. But this is an example of splitting the atom there by bombarding it with a neutron. And that's the fission reaction, or one example of a fission reaction. And this is what's going on in the power plants. What's interesting about it is that just starts the process. As you start that process, the neutrons get released in the transmutation, and then they strike other nuclei, and you get the process occurring over and over and over. This kind of process continuing is called a chain reaction, and we kind of see that here down at the bottom. We see the initial thing, we see neutrons coming out. These neutrons can go back and hit, in this case, it's uranium-235, can hit that, and you get this chain reaction. And kind of depending upon how that's controlled or not controlled leads to different, either good things or bad things. This is just another kind of cartoon of that. You have a nucleus, neutron comes in, hits it, splits the atom. As you split, you have two neutrons from that fission reaction, and then those become involved, hitting it just kind of on and on and on. So the minimum mass that you need in order to sustain a chain reaction is called the critical mass. If you get more than the critical mass, then that's called a supercritical mass. And then you can get an explosion. And so if you have the smaller amounts and you keep them separated and then push them together, then you can get to that supercritical mass. And some of the weapons were done that way, some of the early weapons. So this is why I was saying is that subcritical mass, critical mass, supercritical mass, depending upon getting that mass where you want it, depending upon what you want your outcome to be, is really important. Let's talk about fusion. So in fission, remember, we were talking about splitting the atom. Fusion, as you can imagine, if you're fusing things together, you're putting them together. And so in fusion, it's those lighter elements, as we talked about. We're putting those together to form heavier elements. So in this process, just like in the fission, the products have higher nuclear binding energies, so energy is released. Fusion, though, has about 10 times more energy per gram than fission. So just as we did that calculation early on showing that, gosh, fission has a lot of energy that's released, fusion is even more. And fusion is what goes on in the sun. And so that's the basis of the sun's energy, is fusion. That's also the basis of some of the more modern nuclear weapons as well. So what are some of the advantages of fusion? Well, you could do pretty much limitless energy if you could figure out how to do it appropriately. You don't have a lot of the radioactive waste products. So one of the negatives to fission is you get radioactive waste, and the half-lives on those are really long. So basically there's nothing, you just bury it somewhere and it just sits there. The other thing that's interesting about this is deuterium. So deuterium is the isotope of hydrogen. Is the deuterium in water is in water, and that's a reactant to form this. And so there's a lot of that around. The disadvantages, you need really high temperatures to make it work, and how do you contain this? So materials to contain it, and that's a problem. And then current production methods consume more power than they produce. So long way from there. Radiation in the environment. So we are exposed to radiation. You hear about this stuff in the news every so often, but what's important to remember is there's two types of radiation, ionizing and non-ionizing. So ionizing, that would harm people or harm living things, but non-ionizing, the example here is radio frequency radiation. That doesn't have enough energy in there or enough penetrating power to cause a problem. The ionizing radiation, one of the negatives to that is because most living things have a lot of water in it, you can form hydroxide radicals, OH radicals, and we see that down at the bottom here. And it is known that those OH radicals can cause some cell damage. And so that's why ionizing radiation you have to be careful about, because it can cause cell damage. When we talk about some of the units, when we talk about radiation exposure, gray is one, and then the one that probably people are more familiar is rad, and that's the radiation absorbed dose. And so you'll hear people talk about rads and that. There's actually a calculation that can be done, and then you can figure out something called relative biological effectiveness. And that is a scale to tell you how harmful the radiation is with respect to tissue. And you think tissue is important because that's usually living organisms, us included. Another phrase that you'll hear is for effective dose is called a rim. And then this rim can factor into with the RADs and the RBE, and those are all kind of interrelated when people talk about some of this stuff. Okay, that kind of wraps up the nuclear chemistry part. There's a little more detail on some of this latter stuff in the book if you're really interested in reading about it. Here are some some homework problems I would suggest you take a look at. Most of them center around balancing equations and things like that. The big thing to remember on that, once again, is you're changing what the element is. So you got to look it up in the periodic table to see what the new element is. And so don't forget to do that. And then remember that we're balancing atomic mass, the top number, and we're balancing atomic number, the bottom number. So any questions about any of the nuclear chemistry stuff? Okay, so once again, Thursday during class time, go to Canvas, take the exam covering chapters 24 and 21. Next week on Tuesday at 8 a.m., go online and take the final exam. That final exam is comprehensive, so this covers the whole chapter. And then the final thing is just, once again, I appreciate you taking the class. Enjoyed teaching you. I hope you enjoyed the class. And just a couple more exams to go, then you'll be finished. So keep studying and get ready for these next 2 tests. Thank you.